So today I'm going to talk about the ultra high temperature composites thermal protection system in extreme environment. So this is a very hot topic right now. So let me begin my presentation. Well, before I talk about composites thermal protection system, I'm going to introduce myself, a little bit background. So I'm a professor in mechanical aerospace, and my research is in composite materials and structures, and also manufacturing. Teaching-wise, I've been teaching different type of courses, many in mechanics, materials, manufacturing. Actually, I just finished my 15-year. I'm going to get to my 15 years service at UCF. And I started Composite Snap in 2007 when I was hired, at that time. So we have been working with different government agencies and industrial companies, do all kinds of composites research. So let me move to our topic today. Well, first of all, you may ask why composites? And so this is the Artemis program and the roadmap. So where we are right now, so now in 2022, actually NASA is planning to have a return to moon 2024. And after 2030, we may reach to Mars. And so this is our roadmap according to Artemis program. If you look at the cost-wise, one of the challenges is cost. If you send 1 pound of the payload to no Earth orbit, that costs $1,000, like an International Space Station. However, if you want to send 1 pound of the load to Mars, it costs $1 million. So let's imagine that we have a manned crew to the Mars. We have to carry the food. We have to carry the air. We have to carry the space. Well, most important, we have to carry the fuel. So that costs about $1 billion. Right? So that's why composites can play a very important role because it's lightweight, high performance. Right? Especially, we can reduce the fuel cost, reduce the weight of the spacecraft. And for re-entry vehicles, actually one of the applications I'm going to focus on today is for re-entry vehicles, right? So we put those very heavy ablative composite thermal protection system on the entry vehicles. Actually, I do have a small video clip here. Let me see if I can share with you. Let's put back a little bit. Okay, so let me stop share the video here. So that video is about the entry and descent and landing. So you can imagine that how hot on the surface of the space probe. Right? Another application is non-ablative thermal protection system for hypersonic vehicle. Right? And you can say actually most of the challenging parts is a leading edge. The temperature is extremely high, heat flux is very high. So we're looking for some materials on the leading edge, the very sharp leading edge, which can handle very high temperature, high heat flux. Actually, most important, the core is very sharp. The radius is as small as 1 millimeters. So those are technical challenges from materials point of view. And let me back to ablative composites thermal protection system. Just as you say from the video, we have very hot surface from aerodynamic heating, and the temperature is in range 1800 to 2500 degrees C. And very inner side is cold side. We have to make sure temperature is less than 100 degrees C. So this zone is decomposition zone. So basically, during the flights, the thermal protection decomposes and then absorbs the energy. And this type of ablative thermal protections are used for reentry vehicles, entry vehicles, and also for solid rocket motors and missile system. Also use a similar type of TPS. Traditionally, we use PICA, the phenolic empiric carbon ablator, as the TPS, and also silicon empiric carbon ablator, and also carbon-carbon composites. So this kind of environment material we're using for the ablative thermal protection stuff. And our research is focused on the nanostructured TPS. So we use the nanomaterials. For example, there have been research using the nanoclay and POS, carbon nanotube, nanofibers for this type of the purpose. So I'm going to present our research idea under this topic. And this picture is Dr. Richard Smalley. He was a chemistry professor from Rice University. And he won the Nobel Prize 1996 in chemistry. Actually, I received this paper, we call it Buckypaper, 20 years ago when I was a Ph.D. student. So the idea was to use this paper as the reinforcement for composites. So here, I'm going to talk about the story, how we use this Buckypaper for heat shields. So when we received this paper, it's about 1 inch. And we look at it under a microscope, AFM, and you'll find this is a porous materials with so many carbon nanotubes, single carbon nanotubes. And so from there, we use this Buckypaper as heat shield. So from this figure, you can say we place this Buckypaper on the top of the thermal protection system. And then we're trying to use as a heat shield. So the main idea is based on these two concepts. So because this Buckypaper, we have very high anisotropic thermal conductivity. So that is good because if you look at the thermal conductivity in plane direction and through thickness direction, they have more than 1,000 times difference. Right? So it can avoid the hot spots on the surface of the vehicles. Another concept is based on the high strength and the high charge formation of the Buckypaper for mechanical integrity. So lots of time when you look at the reentry vehicles, hypersonic vehicles, it's subject to very high compressive loads and shear loads. So mechanical integrity of the thermal protection system is very questionable. So we're trying to optimize and control the structures, microstructures, nanostructures, and also the properties of this Buckypaper to make it adaptable for the heat shield applications. So that is the whole idea. We utilize this very unique paper as a heat shield for space vehicles or hypersonic vehicles. Actually, we did some work in our lab, and this is called Oxy-acetylene touch tests. And so basically, we create the flame, the temperature at different locations of flame will be different. The outer envelope, it could be high as 1260 degrees C, and the inner core could be 3000 degrees C. So we can control the distance. We place our Buckypaper composites here and then we adjust this distance. You can get different heat flux. If you put this composite so close, you can get very high heat flux, like 1200 watts per centimeter square. So this is the test rig we use in our composite snap. Actually, I do have a quick video here, so hopefully it can work. So we basically apply the flame in front of this panel and monitor the back temperature of the composites. And you can tell the difference with this Buckypaper heat shield and without this heat shield would be different. And this is without the heat shield. This is with heat shield. So you can significantly drop the backside temperature to meet the performance requirement. And also we're working with the company, use plasma jet torch tests, use plume of the liquid rocket engine to test its materials under high velocity, and also inject with a particle to look at the particle erosion. So there are more experimental work going on. And also we developed a code to analyze the efficiency of this heat shield. So this is very simple code based on the one-dimensional problem. Right? We look at the high heat flux from the front, and we create the temperature profile, mass loss profile, and also the mechanical properties, residual mechanical properties. So basically, a little bit background here, we use the energy equation based on the conduction, heat flux, and convection, and also the polymer decomposition for the energy equation. And mass balance is based on the gas flowing out from the heat shield, a residual char, and also the flow out of the char. We use a Darcy snore to model the gas flow. So most important parameter is permeability of this Buckypaper. And polymer decomposition, we just use a Reynolds equation. Right? So there are some sample results. Actually, this is based for the residual modulars, right? Under the aerodynamic heating, under the high heat flux, what is the instant modulars of the thermal protection system. So we set up these models and write the code, use finite elements. You can predict the temperature profile through the thickness. Also, we can find out the backside temperature, cold side temperature, with this heat shield, without that heat shield. And also, mass residuals and residual modulars. So we can analyze the residual properties of the thermal protection system. The last slides I'm trying to share here, our current research, ongoing research, and also the future plan under this topic. So currently we still work on the high temperature fibers for composites, and also work on the 3D ablative composites, and also work on the polymer and ceramic combined with hybrid composite system. And also we'll look at the multifunctionalities, of the TPS, have high aerothermal properties, also electromagnetic performance, such as the radar absorbing or radar penetration properties. And manufacturing-wise, that's kind of the research direction right now. There's 3D printing of the thermal protection system, and also uncertainty and quantification of the TPS. And design-wise, and there are lots of the tools we can integrate the materials, structures, and performance process together. And also the TPS design based on, especially topology design, based on the AI and machine learning. And also sensor system for structure health monitoring and in-space repair. So there are also some suggestions under this topic. And this is my last slides. I have very limited time. So those students are working in my composites group that work on the project. And we got support from FAA. Actually, recently, we received the UCF IR seed grant, work with Subis, and also Artem from Nanostructured Center. Okay, well, I have a little time. Thank you so much for your time to attend my presentation. Please feel free to ask a question.